we see a band of light stretched across the night sky. It looks still, permanent, like paint on a canvas. But we are inside something moving. The Milky Way is a barred spiral galaxy. We observe it from within, not from outside. This internal viewpoint makes its structure harder to map than distant galaxies we can see in full. Astronomers must piece together the galaxy's shape from our position embedded inside it. They use indirect measurements, observations across different wavelengths of light. It is like trying to draw a map of a forest while standing among the trees. The visible disk of the Milky Way measures roughly 100,000 to 120,000 light-years across. This disk contains most of the galaxy's stars, most of its gas and dust. The material arranges itself in spiral arms that wind outward from the center. The disk itself is relatively thin compared to its width, only about 1,000 light-years thick at the spiral arms. This flattened structure formed as the galaxy's material collapsed and began rotating billions of years ago. Beyond the disk lies a much larger halo. It extends several 100,000 light-years in all directions. This halo is roughly spherical. It surrounds the entire galaxy. The halo contains ancient stars, many grouped in globular clusters that orbit far above and below the galactic plane. It also holds diffuse hot gas and, crucially, dark matter that makes up most of the galaxy's total mass. Recent simulations suggest the dark matter halo may extend nearly 2 million light-years from the galactic center. Astronomers estimate the Milky Way contains between 100 and 400 billion stars. The wide range reflects the difficulty of counting stars hidden by dust and distance. Dense clouds of interstellar material block visible light. This makes it impossible to see through the entire galaxy using optical telescopes alone. Radio and infrared observations help fill in the gaps, but uncertainties remain large. Some regions are simply too obscured or too distant for current instruments to survey completely. From Earth, the Milky Way appears as a band of light across the sky. This is because we are looking along the plane of the disk from inside it. When you look toward the galactic center in the constellation Sagittarius, the Milky Way appears brightest, densest. You see progressively fewer stars. Your line of sight extends toward the galaxy's outer edge. The hazy appearance comes from countless individual stars, too faint and distant to distinguish with the naked eye. They blend together into a continuous glow. The Sun orbits the center of the Milky Way at about 220 to 240 kilometers per second. At this speed, the Sun travels roughly 800,000 kilometers every hour. This motion is part of the galaxy's overall rotation. Stars at different distances move at different speeds. The Sun lies about 26,000 to 28,000 light-years from the galactic center, roughly halfway out toward the edge of the disk. Despite this tremendous velocity, our motion through the galaxy is imperceptible in human lifetimes. The distances involved are so vast. One full orbit around the galactic center takes roughly 225 to 250 million years. This span of time is known as a galactic year. It dwarfs any human timescale, spanning geological epochs. The entire recorded history of complex life on Earth. The last time the Sun completed an orbit, dinosaurs had not yet appeared. The supercontinent Pangaea was beginning to form. Since its formation about 4.5 billion years ago, the Sun has completed only about 20 to 23 galactic orbits. On galactic timescales, our solar system is relatively young. Many stars in the Milky Way are far older. They have circled the galaxy dozens more times. The galaxy itself formed roughly 13.5 billion years ago, making it nearly as old as the universe. Our solar system is a late arrival in the galaxy's long history. As it travels, the Sun moves up and down relative to the galactic plane. This vertical oscillation gives its path a gentle wave-like motion through space. The Sun does not simply circle the galactic center in a flat orbit, not like a planet around a star. Instead, it rises above the disk, crosses back down through the plane, dips below it, and then rises again in a continuous cycle. Each oscillation takes tens of millions of years to complete. The motion is driven by the galaxy's overall gravitational field, particularly the gravitational pull of the disk's mass. Currently, the Sun lies slightly above the galactic plane, moving gradually upward. Over the next several million years, it will reach a peak height of perhaps a few hundred light-years above the disk. Then, gravity pulls it back down again. The Milky Way's spiral arms are not solid structures made of fixed stars. They are density waves moving through the disk. This distinction is crucial to understanding how spiral galaxies work. The arms represent regions where matter temporarily concentrates, not permanent groupings of stars that rotate together. Stars pass through spiral arms, rather than remaining inside them permanently. Over time, they drift in and out of these regions. They follow their individual orbits around the galactic center. A star might spend tens of millions of years inside a spiral arm. Then it emerges on the other side, continuing through less dense regions of the disk. The spiral pattern itself rotates at a different speed than the stars, creating the wave-like compression zones. Gas clouds become compressed as they enter spiral arms. This compression triggers bursts of star formation. The increased density causes parts of the clouds to collapse under their own gravity, fragmenting into clumps that eventually ignite as new stars. This is why spiral arms often appear bright and blue in images of galaxies. They are filled with young, hot stars that formed recently from the compressed gas. The Milky Way's spiral pattern is uneven and fragmented. Its arms split, fade, and reconnect, rather than forming a perfect pinwheel. Astronomers have struggled to map the exact number and structure of the arms because of our embedded position and the irregularity of the pattern. Some regions show clear spiral features, others appear more chaotic. The galaxy does not exhibit the clean, symmetrical spirals seen in textbook illustrations. The Sun resides in a smaller feature called the Orion Spur. This spur lies between two major spiral arms, the Perseus arm and the Sagittarius arm. It is not one of the galaxy's dominant structures, just a minor concentration of stars and gas extending a few thousand light-years. The Orion Spur contains many familiar nearby stars and stellar nurseries, including the Orion Nebula, from which it takes its name. Our position in this relatively minor structure means we are not in one of the galaxy's most active or densely populated regions. At the galaxy's center lies a supermassive black hole, about 4 million times the Sun's mass. Known as Sagittarius A, it exerts a strong gravitational influence on nearby stars. The black hole itself is invisible, but its effects on surrounding matter reveal its presence. Material falling toward it heats up, emits radiation across the electromagnetic spectrum. Though the black hole is relatively quiet compared to the active galactic nuclei found in other galaxies, Stars near the center orbit at extreme speeds. Some complete an orbit around Sagittarius A in as little as a few years, moving at several % of the speed of light. Their motion provides direct evidence for the black hole's existence, allows astronomers to calculate its mass with precision. By tracking individual stars over decades, researchers have mapped their elliptical orbits. They confirmed that an enormous concentration of mass sits at the exact center of the galaxy. No other explanation fits the observations. The inner Milky Way contains a rotating bar of stars. This bar stretches across the galaxy's central region, tens of thousands of light-years from end to end. Unlike the spiral arms, which are density waves, the bar is a more rigid structure. The stars within it move together as a coherent unit, rotating around the galactic center. Barred spiral galaxies are common in the universe. About 2/3 of all spiral galaxies contain central bars. The Milky Way's bar became clearly understood only in recent decades, because dust and gas obscure our view of the inner galaxy in visible light. Infrared observations penetrate this obscuration, revealing the elongated distribution of stars at the center. The bar channels gas inward toward the core. As the bar rotates, it creates gravitational forces that shepherd gas clouds, pushing them from the outer disk toward the galactic center. This process feeds the central region with fresh material. The gas accumulates in dense molecular clouds near the core. Some of it eventually forms new stars. The bar also helps shape the inner spiral structure. The way gas flows around the bar's ends influences where spiral arms begin, creating connections between the bar and the larger spiral pattern. Evidence suggests the central region was more energetic in the past. Large-scale structures indicate previous episodes of intense activity. Radio observations reveal enormous bubbles of hot gas extending above and below the galactic plane. These bubbles stretch tens of thousands of light-years. They appear to have been inflated by powerful outflows from the center. The exact cause remains unclear. Perhaps bursts of star formation, or periods when the central black hole was more active, consuming material and ejecting energy. The center is quieter now than it once was. Sagittarius A accretes very little matter in the present era. The intense activity that shaped the large-scale structures appears to have diminished over time. But the galaxy's history is written in these remnants, visible to instruments sensitive to radio waves and high-energy radiation. Stars in the Milky Way orbit faster than visible matter alone can explain. According to classical physics, the galaxy should fly apart. When astronomers measure how fast stars move at various distances from the galactic center, they find something unexpected. Stars far from the center orbit at nearly the same speed as stars closer in. In a system dominated by visible matter, orbital speeds should decrease with distance, like planets in the solar system. The farther out, the slower the orbit. But the Milky Way does not behave this way. The rotation curve stays flat rather than declining. This discrepancy implies the presence of additional mass that does not emit light, mass that cannot be seen directly. The galaxy contains far more matter than we can observe in stars, gas, and dust. Something else is holding it together. The solution is a massive halo of dark matter surrounding the galaxy. This unseen mass provides additional gravity. Dark matter does not interact with electromagnetic radiation. It does not emit light, does not absorb it, does not reflect it. Its presence is inferred entirely through gravitational effects on visible matter. The way stars and gas move reveals the dark matter's influence. Dark matter outweighs the galaxy's visible matter by several times. Most of the Milky Way's mass is therefore invisible. The dark matter halo extends far beyond the visible disk, enveloping the entire galaxy in an enormous spherical cloud. Without dark matter, the Milky Way would not remain stable. Its structure depends on this hidden component. Despite its importance, the nature of dark matter remains unknown. It is not ordinary matter. Dark matter is something else entirely. Dark matter outweighs the galaxy's visible matter by several times. Most of the Milky Way's mass is invisible. Estimates suggest that for every unit of ordinary matter in the galaxy, there are 5 to 10 units of dark matter. The visible stars, the gas, the dust, these are merely a small fraction of the total. The dark matter halo extends far beyond the visible disk, enveloping the entire galaxy in an enormous spherical cloud. Recent simulations suggest this halo may stretch nearly 2 million light-years from the galactic center, far larger than the disk we can observe. Without dark matter, the Milky Way would not remain stable. Its structure depends entirely on this hidden component. The spiral arms would unwind. Stars in the outer regions would drift away into intergalactic space. The gravitational binding that holds the galaxy together comes mostly from dark matter, not from the stars we see. The galaxy as we know it could not exist without this invisible scaffold. Every structure we observe, every spiral arm, every star cluster, all of it is shaped and held in place by dark matter's gravity. Despite its importance, the nature of dark matter remains unknown. Decades of research have not identified what it is made of. It is not ordinary matter, not protons, neutrons, and electrons. Those would interact with light in detectable ways. We would see them. Dark matter is something else entirely, a form of matter that pervades the universe. It interacts with ordinary matter almost exclusively through gravity. No other force seems to affect it. No electromagnetic interaction. No strong or weak nuclear force that we can detect. Physicists have proposed many candidates: weakly interacting massive particles, axions, primordial black holes. Experiments deep underground search for dark matter particles passing through detectors. So far, none have been conclusively identified. The mystery endures. Understanding what dark matter is remains one of the great unsolved problems in physics and cosmology. It shapes galaxies, determines the structure of the universe, yet its fundamental nature eludes us. The halo contains ancient stars and globular clusters. These objects orbit far above and below the galactic plane. Globular clusters are dense, spherical collections of stars. Each cluster contains hundreds of thousands of stars packed into a region only a few dozen light-years across. The Milky Way has more than 150 globular clusters in its halo. They orbit the galaxy in elliptical paths, swooping high above the disk, plunging down below it, then rising again. Many halo stars did not originate in the Milky Way. They were captured during past mergers with smaller galaxies. When a small galaxy falls into the Milky Way's gravitational well, tidal forces tear it apart. Its stars scatter. Some join the disk, others are flung into the halo. Their orbits and chemical compositions reveal their foreign origins. The halo preserves the earliest stages of the galaxy's formation. It acts as a record of ancient events. Some halo stars are nearly as old as the universe itself. formed more than 13 billion years ago. Their chemical simplicity reflects the early cosmos, when heavy elements were scarce. These stars contain mostly hydrogen and helium, very little of anything else, because the universe had not yet produced much carbon, oxygen, or iron. The halo extends far beyond the visible edge of the galaxy. It defines much of the Milky Way's true size. While the disk measures 100,000 light-years across, the halo stretches several 100,000 light-years, perhaps more. If you could see dark matter, the Milky Way would appear as an enormous sphere, not a flat disk. The disk we observe is just the inner, visible region, embedded within a much larger structure that remains invisible to our eyes. The halo contains ancient stars and globular clusters. These objects orbit far above and below the galactic plane. While the disk rotates in a relatively flat configuration, halo objects follow elliptical paths. They swoop high above the disk, plunge down below it, then rise again. Globular clusters are dense, spherical collections of stars. Each cluster contains hundreds of thousands of stars, packed into a region only a few dozen light-years across. The density at their centers is extraordinary. Stars separated by distances smaller than our solar system. The Milky Way has more than 150 globular clusters in its halo, perhaps more than remain undiscovered. Obscured by dust, or simply too faint and distant to detect, these clusters orbit the galaxy in paths that take them far from the disk. Some venture hundreds of thousands of light-years from the galactic center. Their orbits are tilted at random angles, not aligned with the disk's rotation. Many halo stars did not originate in the Milky Way. They were captured during past mergers with smaller galaxies. When a small galaxy falls into the Milky Way's gravitational well, tidal forces tear it apart. Its stars scatter. Some join the disk, others are flung into the halo, following chaotic orbits that reveal their violent capture. Astronomers can identify these captured stars by their motion and chemical composition. They move differently than stars born in the Milky Way. Their orbits are retrograde, moving against the disk's rotation, or highly elliptical. Their chemical signatures also differ, elements in ratios that do not match local stars. The halo preserves the earliest stages of the galaxy's formation. It acts as a record of ancient events. While the disk has been continuously recycling its material through star formation and death, the halo remains largely unchanged. A fossil record written in stars. Some halo stars are nearly as old as the universe itself, formed more than 13 billion years ago, when the cosmos was less than 1 billion years old. Their chemical simplicity reflects the early universe, when heavy elements were scarce. These stars contain mostly hydrogen and helium, very little of anything else, because the universe had not yet produced much carbon, oxygen, or iron. Those elements are forged in stars and supernovae, released into space over time. The first stars had almost none of them. By studying the chemical composition of halo stars, astronomers can trace the history of element production in the early galaxy. Each generation of stars adds more heavy elements. The oldest stars show the lowest abundances. The youngest show the highest. The halo extends far beyond the visible edge of the galaxy. It defines much of the Milky Way's true size. While the disk measures 100,000 light-years across, the halo stretches several 100,000 light-years, perhaps more. If you could see dark matter, the Milky Way would appear as an enormous sphere, not a flat disk. The disk we observe is just the inner, visible region, embedded within a much larger structure that remains invisible to our eyes. The halo's extent is difficult to measure precisely. Its outer boundary is not sharp. Instead, the density of stars and dark matter gradually decreases with distance, fading into the space between galaxies. Determining where the Milky Way ends and intergalactic space begins is not straightforward. The Milky Way did not form all at once. It grew by absorbing smaller galaxies over billions of years. The process continues today. Galactic cannibalism is not a catastrophic event, but a gradual accumulation. Small satellite galaxies orbit the Milky Way, slowly spiraling inward. Tidal forces from the Milky Way's gravity pull them apart, stretching them into long streams of stars. Eventually, their material merges with the larger galaxy. Long, stellar streams are the remains of these consumed systems. They trace the paths of past mergers. Astronomers have mapped dozens of these streams winding through the halo. Each one represents a smaller galaxy that no longer exists as a distinct object. The streams can stretch for hundreds of thousands of light years, thin ribbons of stars following nearly identical orbits. Because they all came from the same parent galaxy, torn apart but still traveling together through space. Over time, these streams disperse and fade, their stars mixing into the general halo population. A star's chemical makeup and motion reveal whether it formed locally or elsewhere. These signatures act as galactic fingerprints. Stars born in the Milky Way have one set of chemical abundances. Stars born in dwarf galaxies have another. The ratios of elements like magnesium to iron differ between galaxies, depending on their star formation history. By measuring these ratios, astronomers can identify which stars are native and which are immigrants. Motion also reveals origin. Stars born in the disk move with the galaxy's rotation. Stars captured from other galaxies often move against it, or follow highly elliptical orbits tilted at steep angles. The Milky Way is still growing today. Gas and small satellites continue to fall inward. The Magellanic Clouds, two dwarf galaxies visible from the southern hemisphere, are slowly being pulled toward the Milky Way. In a few billion years, they will likely merge with it. Streams of gas stripped from the Magellanic Clouds already trail behind them, called the Magellanic Stream. This stream stretches across more than 100 degrees of the sky, a vast ribbon of hydrogen gas being drawn into the Milky Way's gravitational field. Future mergers will further alter the galaxy's shape. Galactic evolution is an ongoing process. The Milky Way in a billion years will not look the same as it does today. New material will be added. Structures will shift. Star formation will continue in bursts as fresh gas arrives. The largest merger in the Milky Way's future is with the Andromeda Galaxy. But that lies billions of years ahead. For now, the Milky Way continues its slow consumption of smaller neighbors, growing incrementally, one dwarf galaxy at a time. Stars are born inside cold molecular clouds made mostly of hydrogen. Gravity causes dense regions to collapse. These clouds are enormous, spanning hundreds of light years, containing enough material to form thousands or millions of stars. Within the clouds, denser pockets begin to contract under their own gravity. As they collapse, they heat up, eventually reaching temperatures and pressures high enough for nuclear fusion to ignite. a new star is born. Star formation happens in bursts, not continuously. When a massive star forms and eventually explodes as a supernova, the shock wave can trigger the collapse of nearby clouds, creating a cascade of new star formation. Massive stars live short lives and end in supernova explosions. These events release enormous energy. A single supernova can outshine an entire galaxy for weeks. The explosion ejects the star's outer layers into space at speeds of thousands of kilometers per second. This expelled material carries the star's legacy, everything the star fused during its lifetime: carbon, oxygen, silicon, iron, elements that did not exist when the star was born.
Supernovae forge heavy elements like iron and gold.
These elements did not exist in the early universe. The Big Bang produced only hydrogen, helium, and traces of lithium. Everything heavier was created inside stars. During a star's life, nuclear fusion in its core builds progressively heavier elements. Hydrogen fuses into helium, helium into carbon and oxygen. In the most massive stars, the process continues: carbon into neon, neon into magnesium, silicon into iron. But iron is the end of the line. Fusing iron consumes energy rather than releasing it. Once a massive star's core fills with iron, fusion stops. The core collapses in less than a second. The collapse triggers a supernova explosion. In that violent event, conditions become extreme enough to forge elements heavier than iron: gold, platinum, uranium. These elements are created in the final moments of a star's life and scattered into space by the explosion. Some of the heaviest elements are created in even more violent events, when two neutron stars collide and merge. These collisions produce bursts of gamma rays visible across the universe, and they spray newly formed heavy elements into the surrounding gas. The expelled material becomes part of future stars and planets. Matter is recycled across generations. The iron in your blood was forged in a star that exploded billions of years ago. The calcium in your bones, the oxygen you breathe, all of it created in stellar furnaces and released into space through supernovae. Star formation in the Milky Way has slowed over time. The galaxy's peak star formation occurred billions of years ago, when the disk contained more gas and experienced more frequent mergers with smaller galaxies. Each merger brought fresh material and triggered bursts of new star formation. Today, the rate has declined. The Milky Way forms only a few new solar masses of stars per year, compared to tens or hundreds of solar masses per year in its youth. The available gas has been partly consumed, partly ejected by supernovae and stellar winds. However, new stars continue to form. Stellar nurseries like the Orion Nebula remain active. Regions where dense molecular clouds are collapsing into clusters of young stars. These nurseries glow with the light of newborn stars, hot and bright, ionizing the surrounding gas. The process will continue for billions of years, as long as gas remains available. The Milky Way has not yet exhausted its fuel for star formation. Though the pace has slowed, the galaxy is not finished creating stars. Molecular clouds where stars form can be enormous. Some span hundreds of light years and contain enough material to form millions of stars. These giant molecular clouds are among the most massive structures in the galaxy, weighing millions of times the mass of the Sun. Within these clouds, temperature and density vary. The densest cores become stellar nurseries, while less dense regions remain as diffuse gas and dust. The clouds are not uniform. They are clumpy, filamentary, threaded with magnetic fields that shape their structure. Gravity competes with other forces. Magnetic pressure resists collapse. Turbulence stirs the gas. Radiation from nearby stars heats and disperses material. Only in regions where gravity overcomes these opposing forces do new stars form. The balance determines where and when star formation occurs. It is not a simple process, but a complex interplay of physics that varies from cloud to cloud. Different types of stars have vastly different lifespans. Massive stars burn through their fuel quickly. A star 50 times the Sun's mass may live only a few million years. Small stars burn slowly. A red dwarf with a tenth of the Sun's mass can shine for trillions of years, longer than the current age of the universe. Some stars are ejected at speeds high enough to escape the galaxy. These are known as hypervelocity stars. They travel at hundreds or even thousands of kilometers per second, fast enough to break free from the Milky Way's gravitational pull entirely. Most hypervelocity stars are thought to originate near the galactic center, where the supermassive black hole's gravity can accelerate them to extreme speeds. A binary star system approaches too close to the black hole. Tidal forces tear the pair apart. One star falls toward the black hole. The other is flung outward at tremendous velocity. A gravitational slingshot effect. These stars race through the galaxy at speeds that will eventually carry them into intergalactic space. They will wander alone between galaxies, orphaned from their birthplace, no longer bound to any galactic system. In dense regions, stars can pass close enough to collide. Such events are rare, but possible. The galactic center contains some of the densest stellar environments, where stars orbit in crowded clusters around the central black hole. A stellar collision does not resemble two solid objects crashing. Stars are mostly empty space, but their outer layers can merge and strip away. The collision creates a blue straggler, a star that appears younger and more massive than its neighbors because it gained material from another star. When neutron stars merge, they create heavy elements. These collisions are among the universe's most violent events. Neutron stars are the collapsed cores of massive stars, incredibly dense. A teaspoon of neutron star material would weigh billions of tons on Earth. When two neutron stars spiral together and collide, the event produces gravitational waves, ripples in space-time that travel at the speed of light. Detectors on Earth can measure these waves, confirming the collision occurred millions or billions of light-years away. The collision also creates a kilonova, a burst of light powered by radioactive decay of newly formed heavy elements. Gold, platinum, rare earth elements. Much of the galaxy's heaviest material comes from these neutron star mergers. Pulsars emit regular pulses of radiation as they spin. Their precision makes them natural cosmic clocks. A pulsar is a neutron star that rotates rapidly, sometimes hundreds of times per second. It emits beams of radiation from its magnetic poles. As the star rotates, these beams sweep across space like a lighthouse. If Earth lies in the path of one of these beams, we detect a pulse. Regular, predictable. The timing is so precise, that pulsars can be used for navigation in deep space. Some pulsars are part of binary systems, orbiting another star or even another neutron star. By measuring changes in the pulsar's timing, astronomers can detect the gravitational influence of its companion, even if the companion is invisible. Magnetars are neutron stars with the strongest magnetic fields known, 1 trillion times stronger than Earth's magnetic field. These fields are so intense they warp the vacuum of space itself, creating conditions unlike anywhere else in the universe. Magnetars occasionally release bursts of energy, starquakes. The neutron star's crust fractures under magnetic stress, releasing more energy in 1/10 of a second than the sun emits in 100,000 years. Shockwaves from supernovae can trigger new star formation. Destruction and creation are linked. When a massive star explodes, the expanding shell of gas slams into nearby molecular clouds, compressing them. This compression can push the cloud past the threshold where gravity takes over, causing it to collapse and form new stars. The cycle continues. Stars form, live, die, and in dying, they seed the birth of the next generation.
The Milky Way is surrounded by a vast halo of hot gas. This gas extends far beyond the disk, reaching temperatures of millions of degrees. Too hot to form stars, too diffuse to emit much visible light. The hot halo was discovered through observations in X-rays and ultraviolet light, wavelengths that reveal high-temperature gas invisible to optical telescopes. This gas contains as much mass as all the stars in the disk combined, yet it remains largely hidden. The origin of this hot gas is debated. Some may be material expelled from the disk by supernovae and stellar winds, heated to extreme temperatures and blown outward. Some may be primordial gas left over from the galaxy's formation, never cool enough to collapse into stars. This hot halo may serve as a reservoir, slowly cooling and falling back onto the disk over billions of years, replenishing the supply of gas available for star formation. A galactic recycling system, operating on timescales far longer than human comprehension. Magnetic fields thread through the galaxy. They influence gas motion and cosmic rays. These fields are weak compared to a refrigerator magnet, but they span thousands of light years. Their total influence across such vast distances becomes significant. Magnetic fields shape the structure of molecular clouds. They guide the flow of ionized gas. They affect how energy from supernovae and stellar winds propagates through the galaxy. Without magnetic fields, the Milky Way would behave differently. Astronomers map these fields by observing polarized light from stars and by measuring the alignment of dust grains in interstellar space. Dust grains align with magnetic field lines. Their orientation reveals the field's direction. The galaxy's magnetic field has a large-scale structure, roughly aligned with the spiral arms. But it also contains turbulent, chaotic regions, where local processes disrupt the overall pattern. High-energy cosmic rays travel through the Milky Way constantly. Some pass through Earth every second. Cosmic rays are not rays, but particles, mostly protons, some heavier atomic nuclei, accelerated to nearly the speed of light. The most energetic cosmic rays originate outside the galaxy, from distant sources like active galactic nuclei or gamma-ray bursts. Lower-energy cosmic rays are produced within the Milky Way by supernova remnants and other violent events. These particles spiral along magnetic field lines, bouncing between regions of the galaxy. Their paths are so twisted
that tracing them back to their sources is nearly impossible. Even though they move at almost light speed, they take millions of years to escape the galaxy. Cosmic rays affect star formation. They ionize gas in molecular clouds, influencing the cloud's internal pressure. The galaxy emits light across the electromagnetic spectrum, many wavelengths invisible to human eyes. Radio waves reveal cold hydrogen gas. Infrared light penetrates dust to show star formation. X-rays trace hot gas. Gamma rays mark violent events. To understand the galaxy fully, astronomers must observe at all wavelengths. Visible light alone captures only a fraction of the story. Neutrinos pass through the galaxy almost without interaction. They carry information from extreme cosmic events. Neutrinos are nearly massless particles that interact only through the weak nuclear force. Trillions pass through your body every second from the sun. You never feel them. Neutrinos from supernovae can be detected. When a massive star collapses, most energy is released as neutrinos, not light. Neutrino astronomy opens a window into processes that light cannot reveal. They carry direct information from the cores of exploding stars.
Planetary systems form naturally around stars. They are common throughout the Milky Way. When a star forms from a collapsing cloud, not all the material falls onto the star. Some remains in a rotating disk around it. Within this disk, dust grains collide and stick together, building larger and larger clumps. Pebbles become boulders. Boulders become planetesimals. Planetesimals grow into planets. The process takes millions of years, but it appears to be robust. Nearly every star observed in sufficient detail shows evidence of planets or the disks that form them. Planetary systems are not rare exceptions. They are the natural outcome of star formation. Thousands of exoplanets have been discovered, planets orbiting stars other than the Sun. They come in remarkable variety. Gas giants larger than Jupiter, orbiting closer to their stars than Mercury orbits the Sun. Rocky planets, several times Earth's mass. Worlds covered in water. Planets with atmospheres unlike anything in our solar system. The diversity suggests that planetary formation is flexible. Many outcomes are possible, depending on the conditions in the protoplanetary disk. The distance from the star, the amount of material available, the presence of nearby massive planets that shape the disk through gravity. Many planets drift freely without a parent star. These rogue planets roam the galaxy alone, ejected from their original systems or formed in isolation. Once ejected, they travel through the galaxy indefinitely. Their surfaces frozen, dark. Estimates suggest billions of rogue planets exist in the Milky Way, but they are difficult to detect. Organic molecules are widespread in interstellar space. They form in stars and cold clouds. Astronomers have identified hundreds of different molecules in space, including amino acids, the building blocks of proteins. These molecules form through chemistry on dust grain surfaces. Some are simple: water, ammonia. Others are complex: chains of carbon atoms, dozens of units long. The presence of these molecules suggests that the raw materials for life are abundant. Scattered throughout the galaxy, in clouds, in comets, on asteroids. Certain regions of the galaxy may be more favorable for complex life. Factors include radiation levels and element abundance. Too close to the galactic center, intense radiation may disrupt planetary atmospheres. Too far out, heavy elements become scarce. The Milky Way may contain a broad galactic habitable zone. Earth lies within this region, far enough from the center to avoid excessive radiation, close enough that heavy elements are abundant. Whether life exists elsewhere remains unknown, but the ingredients are present.
The galaxy contains hundreds of billions of stars, likely trillions of planets. The search for life focuses on planets in habitable zones, where liquid water can exist. Earth had the right conditions. How many other worlds do remains uncertain. Planetary atmospheres vary dramatically. Some exoplanets have atmospheres thicker than Jupiter's. Others have been stripped away entirely by their star's radiation. The composition matters as much as the presence. Carbon dioxide, methane, oxygen. Each gas tells a story about the planet's history and potential for life. Detecting biosignatures in distant atmospheres is difficult, but possible. Oxygen in large quantities might indicate photosynthetic life. Methane combined with oxygen is especially intriguing. These gases react and destroy each other. Finding both together suggests something is continuously producing them. Future telescopes will analyze exoplanet atmospheres in detail, searching for these chemical hints of life. The galaxy may be full of living worlds, or Earth may be rare. We do not yet know. The Milky Way will merge with the Andromeda Galaxy in about 4 to 5 billion years. This encounter is already underway. The two galaxies are approaching each other at roughly 110 kilometers per second. Pulled together by mutual gravitational attraction, Andromeda is the largest galaxy in the local group, about twice as massive as the Milky Way. It contains roughly 1 trillion stars, compared to our few hundred billion. From Earth, Andromeda appears as a faint smudge in the night sky, visible to the naked eye under dark conditions. But it is racing toward us. The distance between the galaxies shrinks by about 300,000 kilometers every day. The merger will distort both galaxies dramatically. Their shapes will change over billions of years. Computer simulations show the process in detail. The galaxies will approach, pass through each other, swing back around, and collide again. Each passage pulls long tidal tails of stars from both galaxies, streams of stars flung into space by gravitational forces. The collisions will not be gentle, but they will be slow by human standards. The first close passage will occur in about 4 billion years. The Sun will still exist then, though it will be older, hotter. Earth's oceans may have already boiled away by that time. During the merger, the night sky will transform. Andromeda will grow larger and larger over millions of years, eventually filling a significant portion of the sky. New bursts of star formation will ignite across both galaxies as gas clouds collide and compress. The sky will blaze with young blue stars. Direct star-to-star collisions will be extremely rare. The vast distances between stars prevent frequent impacts. Even in the densest regions of both galaxies, stars are separated by light years. Space is mostly empty. When two galaxies merge, their stars pass by each other like two swarms of gnats. Individual encounters are unlikely, but the overall gravitational field reshapes everything. Stars are flung into new orbits, some ejected into intergalactic space, others pulled toward the merging cores. The solar system will likely survive intact. Simulations suggest it will be thrown into a different orbit, perhaps farther from the galactic center than it is now, perhaps closer. The Sun's position in the new galaxy is uncertain, but the system itself should remain bound together. The distances between planets are small enough that external gravitational forces will not tear them apart. Earth will continue orbiting the Sun. Star formation will continue after the merger. The combined galaxy will remain active. Gas from both galaxies will mix, providing fuel for new generations of stars. The central supermassive black holes from both galaxies will eventually merge, creating a single black hole more massive than either. This process releases enormous energy, gravitational waves rippling through space-time, detectable across the universe. The final product will be an elliptical galaxy, not a spiral. The merger will scramble the ordered rotation of both disks. Stars will move in random orbits. No clear spiral structure will remain. Astronomers have named this future galaxy Milkomeda, a combination of Milky Way and Andromeda. It will be one of the largest galaxies in the local group, dominating the local cosmic neighborhood. The Milky Way's current spiral form is temporary. Galaxies evolve over cosmic time. What we see now is just one phase in a long history. The galaxy has changed before. It will change again. The merger with Andromeda is not the end. Other galaxies in the local group will eventually join. Over tens of billions of years, the local group may collapse into a single massive galaxy, but still evolving.
Astronomers understand many distant galaxies better than the Milky Way. Studying our own galaxy is uniquely difficult. We cannot step outside to see its shape. We are embedded within it. Observing from inside means dealing with obscuration. Dust blocks visible light in many directions. The galactic plane is particularly opaque. Whole regions remain hidden from optical telescopes. Astronomers must use multiple wavelengths to build a complete picture. Radio waves penetrate dust. Infrared light reveals what visible light cannot. X-rays trace high-energy processes. Much of what we know is inferred indirectly. Motion, gravity, and light reveal unseen structures. The rotation curve tells us about dark matter. Stellar velocities map the galaxy's mass distribution. Chemical abundances trace the history of star formation. Mapping the Milky Way is an ongoing project. New surveys add detail every year. The Gaia mission has measured positions and motions for billions of stars, creating the most detailed map of the galaxy ever made. These surveys reveal structures that were previously unknown: stellar streams from ancient mergers, subtle warps in the galactic disk, concentrations of stars that hint at the galaxy's violent past. The Milky Way is changing even now. Its evolution has not stopped. Small galaxies continue to fall in. Stars are born and die. The spiral arms shift position over millions of years. Our solar system is a small component of a vast system. It plays no special role in galactic dynamics. The Sun is one star among hundreds of billions, orbiting in the outer disk, not near the center, not at the edge, somewhere in between. The solar system's orbit is relatively circular and stable. It does not venture into the most dangerous regions, the galactic center with its intense radiation, or through the densest spiral arms where supernovae are frequent. This stability may have been important for life on Earth, avoiding catastrophic radiation events, maintaining a relatively constant environment for billions of years, long enough for complex life to evolve. The Milky Way remains both our home and a scientific mystery. Understanding it helps explain galaxies everywhere. The processes that shaped the Milky Way are not unique. They occur in galaxies across the universe. Star formation, spiral density waves, dark matter halos, supermassive black holes, galactic mergers. These are common features of galaxy evolution. By studying the Milky Way in detail, astronomers learn about galaxies in general. Our position inside provides unique opportunities. Individual stars can be observed closely, chemical compositions measured precisely, stellar populations analyzed in ways impossible for distant galaxies. Future discoveries will continue to reshape our understanding. New telescopes will probe deeper, reveal fainter structures,
map the galaxy's dark matter distribution more accurately. Questions remain unanswered. How exactly did the Milky Way form? What triggered its spiral structure? How many mergers has it experienced? What lies in the regions we still cannot see? The galaxy contains mysteries we have not yet uncovered, structures we have not detected, processes we do not fully understand. But every observation brings new insight. Every survey adds detail to the map. The Milky Way is vast, ancient, complex, and we are inside it, looking out, trying to understand the whole from our small corner of the disk. We see a band of light stretched across the night sky. It looks still, but we know now what it is: a spiral galaxy in motion, rotating, evolving. Our home in the cosmos.